planes and roundabouts. The other way in which gravity is different from the force of the standard model is related to the way it is understood within the Einstein theory of general relativity. In this theory, it is questionable whether we should even call gravity a force at all. Really, when getting to the grasp with the Dirac equation for our journey across the map, we saw that a special theory of relativity arises when you insist that the laws of physics are the same for all inertial observers. Observers traveling with a constant speed in a constant direction. The law of physics includes electromagnetism, so that means that the speed of light must be the same for all those observers, and once you insist on that, all the weird effects on how time passes and how spaces contract follow, as does the famous equivalence equation between the energy and mass, E equals mc squared. To get such a astounding new physics from such a general principle is remarkable. But what about other observers? Most of the time we are not inertial observers. Surely the laws of physics should not change just because we are accelerating or decelerating. It is certainly tempting to insist that physics should be the same for all observers, even non-inertial one. Really? If only because we got such a lots of new and correct physical understanding from doing that for the inertial ones. Anyway, it seems intuitively right somehow. That is a challenge Einstein's addressed with his general theory of the relativity. General because it applies to all observers. Yes, general because it applies to all observers, not just to the special case of the inertial ones considered in his previous masterpiece, the special theory of relativity. What are the effects of the acceleration? There is an airport not so far away from us. We will visit this soon on our travels in an airplane accelerating down the runway for takeoff. The passengers feel themselves pressed back into their seats. From their point of view, this feels like a force, and that's why they are not inertial observers. Imagine yourself in their place. The water bottle you left on the floor beneath your seat rolls backwards as though someone is pushing it. Objects in your frame of reference do not move with a constant speed as they should for an inertial observer. From your point of view, objects accelerate backwards. From my point of view, watching from the park, you are accelerating forwards and leaving them behind. Yes. Wow. How does this connect to gravity? Well, imagine it is night. It is pitch black outside. You are pressed back in your seat as the plane accelerates horizontally, but could you tell the difference between this situation and the possibility that an airplane might be flying upwards at some angle and a constant speed? In both cases, the bottle or carelessly stored laptop would accelerate backward until it hit something, maybe the back of the cabin. Einstein's key observation was to notice that it is difficult, perhaps impossible, to tell the difference between the frame which is non-inertial because it is experiencing the gravitational force, the climbing airplane, and a frame which is non-inertial because it is accelerating, the horizontal airplane speeding up. Wow. Similarly, a frame which is falling fully under gravity looks very much like an inertial frame in which no gravity acts. In fact, the only frame we are familiar with which really look inertial are those in the free fall. Most obviously, the frame moving along with the International Space Station. Continually free falling along its orbit around the Earth. Yes. It is worth thinking about the situation of something in orbit like a ISS compared to the someone or something on. For example, the roundabout in the children's playground we just noticed across the park from us. From the point of view of the someone on Earth, the ISS International Space Station is moving quickly and it would move in a straight line according to their conservation of momentum. But for the gravitational attraction between it and the Earth, yes, the gravitational force plays the same role as the arm of a child holding on to the roundabout. Spinning in the playground we can see. By holding on, the child's arm exerts a force that pulls them continually towards the center of the roundabout and so keeps them turning around it. Likewise, if the gravity suddenly stopped working, the ISS would fly off into outer space. But gravity keeps it circling in orbit. Gravity provides a centripetal force. Yes, centripetal force directed towards the center of the Earth. Yes. But there are some big differences between the situation of the child and the ISS. Apart from the obvious ones involving a space suit and stuff. On the roundabout, the child experiences a centrifugal pseudo-force. Yes, centrifugal pseudo-force. They definitely are not in an inertial frame. Anything they drop will fly off the roundabout, away from the axis of rotation, and in the middle. Yes. Yet on the ISS, the astronauts seem to experience fewer forces acting. Not only do they not experience a centrifugal pseudo-force, but they seem to be weightless. Yes, the reason is that in orbit, your weight under the centrifugal pseudo-force completely cancel, leaving you in a free fall. This is very different experience from the being flag around a roundabout. For two main reasons. Firstly, gravity acts on your whole body and indeed all matter equally and simultaneously, so you don't have to grab onto the handle and then have your arms pull the rest of your round the circle. Your arms, legs and the rest are all being acted on by gravity. The second reason goes to the heart of the general relativity and the reason you are on the ISS, in fact, in an inertial frame. The second reason goes to the heart of the general relativity and the reason you are on the ISS, in fact, in an inertial frame. Mass appears in the two important equations. Force is a mass multiplied by acceleration. Yes, Newton's law F equals ma, and the force of the gravity is proportional to the mass. General relativity works because the mass in those two relations is identical. On the face of it, there is no reason that this should be so, but in the general relativity, it is built in. That was another of Einstein's great insights. This means that in your ISS reference frame, the centrifugal pseudo-force can be cancelled by the force of gravity, not just for one particular mass approximately, but for all masses exactly all the time, leaving you in an inertial frame. In fact, because it cancels a pseudo-force in this way, it is legitimate to say that general relativity reduces the force of gravity to the status of just another pseudo-force. Really? Wow. The principle of the conservation of momentum, yes, used to define an inertial frame, still applies and still defines such a frame. But inertial frames now include any frame falling fully under the gravity. Bodies falling fully like this are said to be traveling along a geodesic which is a redefinition in the space and time of the what constitutes a straight line, the shortest route between 2 points. Wow! So bodies falling fully like this are said to be traveling along a geodesic, which is a redefinition definition in a space and time of the what constitutes a straight line. What constitutes a straight line, the shortest route between 2 points. New definition. In the absence of the gravitational field, a geodesic is a straight line in the Euclidean sense. Yes, Euclid was the first person we know about to define rules for geometry. Amongst these rules or axioms is a statement that a maximum number of times pair of the straight lines can cross each other is once, and parallel straight lines never meet each other. If there is no gravitational field around, geodesics are straight lines, and the general relativity, special relativity, and Newton's laws of motion all agree that a fully moving body will travel along the straight line at a constant speed. Yes. But near a large mass, general relativity states that geodesics bend into curves, or even into the closed ellipse of the orbiting ISS. Really? Space and time defined by the geodesics are no longer Euclidean. The very meaning of the straight line has changed. Yes. Maybe the easiest way to get an idea of what's going on is to imagine two people at the equator a few miles apart, setting off due north, parallel to each other. Though they set off parallel and keep traveling in the same direction, due north, they will eventually meet at the North Pole because the surface of the Earth is curved and defines a non-Euclidean two-dimensional geometry. Wow! Near a large mass, a space is curved in 3 dimensions, and the straight lines, geodesics, can become orbits. Yes, this curvature is what we and all other masses experiences as a gravitational force. Really? This is why gravity is, in some sense, a pseudo-force. It is an effect generated by our curves in the geometry of space-time. Yes, this is a very different way of thinking about a force from how we think about the forces in a standard model. If we think of particles and forces as actors on the stage of the space-time, gravity isn't just another actor. It is something which bends the stage on which the others perform. Wow. Also, as is already being discovered in our exploration, the other forces are fully developed in the quantum field theories, while gravity is definitely not. Wow.